So I'm just going to spend a couple of seconds on this because this is identical to the lab we did in class. You pull the cart attached to the string and the spring out to different displacements. So I could say I have the spring here, string, cart, right? And then I pull it out like that. So now I have the spring stretched out, string, cart, right? So this is one, and then next I do this. Yeah. If we take a quick look, what we see is that the spring is pulling this way, right? Spring force, even as I am displacing this way, X. So you know those two always oppose. The X of the spring, the X, right? Let's see if I can erase this. Oh no, apparently I cannot. Okay, so the X of the spring is how much from where it originally was to where it ended up, right? And we know that U spring, or they say elastic potential energy. So that's what, those are the same thing. I like mine better. Equals 1/2 kx squared, right? So, so you pulled it out and then you let go of it. You let go of the cart. Step 2, you let go of the cart. And then in step 3, you see that the cart is pulled, by the spring this way. And we looked at it when the spring was no longer in place. When the spring goes back to its original shape like this, we measured the velocity of the cart. Okay, that's how we did that lab. That's how you do this lab. So the bottom line is U spring in joules versus X in meters. And I can't see in this lab that they actually ask you to do this step, but it should be quadratic because the equation is U spring equals 1/2 kx squared, right? And if energy is conserved, and they say there's no friction on this track or whatever, then if U spring equals 1/2 kx squared, it should equal the EK when the spring is, no longer in play. If we have the full U spring when it's stretched out, that should equal the full EK here. All right, and then if you know, so let's just for funsies say that number is, let's say that number is 100 joules, right? So that means this should be 100 joules. And then if you know 1/2 mv squared, right, you should be able to plot EK, right, in joules versus V, and that would give you a quadratic, and then EK versus V squared would give you a straight line. Now that's probably the next lab. Over here, if I plot U spring versus X, that should give me a quadratic, and U spring, all in joules, versus X squared should give me a straight line. And from each of these, I should be able to find, so if this one is a straight line right here, then Y equals mx plus b, describes it, 0 y-intercept, EK equals, what's the slope? V squared. And so it's pretty easy to go in and say, hey, that's 1/2 m, right? So if I knew that the value for slope was 10 joules per meter squared per second squared, if I knew that, then I could say 10 equals 1/2 m, or 20 equals the mass, right? So 20 kilograms. So I could do it that way. Or I could say, I could do the same thing, right, with this graph over here, right? And I could say, hey, it's linear. Y equals mx plus b. U spring equals, we'll say 0 y-intercept. U spring equals, what's the slope? And then x squared. And we know the slope is, we know the slope is 1/2 k for the spring energy. And so let's say that the slope was 40 joules per meter squared. Then if I said slope 40, right, joules per meter squared equals 1/2 k, then k would equal 80, right? 2 times 40. That's the gist of really both of these labs. I'm going to turn this off for a second, see if there's anything of note. I think most of these, it looks like they just had you go straight to the spring potential versus x squared graph. You know, I would have made you go through choosing to linearize it. Interpreting your graph, I think we just talked about that. Right, the y-intercept is the value of elastic, the intercept, oh, the intercept. Okay, sure. That's worth noting. All right, so let's go back and look. So the y-intercept is just the stretch of the spring. I mean, the energy stored when it's not stretched at all, which should be 0. So that's fine. 0. I would expect a 0 y-intercept. It's parabolic. It's quadratic. Yes, that's correct. We have a graph that shows. We know how to linearize it. Interpreting your linearized graph, I just did that for you. And let's see what else. You're welcome to pause this. Hopefully you know how to find a spring constant. In this case, or this lab, you have to do it on the side. You could also do it hanging. You've certainly done it that way before. So, I mean, if the spring starts here and then you stretch it out to here, in this case, you could put masses on it. And so let's say I add a mass. I'm sure that's what this video is going to do. So this moves down, this pulls it out like this, right? So maybe I add 100 grams. And if I do that, then let's see. If I do that, then what I have is 0.1 kilograms because it's just times 1 kilogram over 1,000 grams. Okay, so 0.1 kilogram. But what I need is the force required to pull this out like this, right? So Fg is what's balancing with the spring force. So equals mg, so it equals 0.1 kilograms times 10 newtons per kilogram. Okay, so then we get right back to what we've known in the past, which is the fact that if they're balanced, so that leaves us with the gravitational force here being 1 Newton. And so if these, if the gravitational force that's, this gravitational force, 1 Newton, is causing the tension here. You could use whatever you want to. So the tension is this, right? And so that means that if the spring is in equilibrium, then the spring force is this, right? So if you know the spring force and you know the stretch, then then you can find K, right? So spring F versus X and the slope is K. That would be in newtons. That would be in meters. So you would do several different versions of this to get this. So I would say just be careful. Things you want to keep straight are EK versus V would be quadratic. Super terrible graph. Sorry, guys. EK, this is in joules, meters per second, right? So if it's quadratic, then the linear graph right here, also a terrible graph, is versus V squared in meters squared per second squared. Watch the units. Yeah, so graphs to know. That one, and this is no doubt what the Puck lab is after. I'm probably not even going to go there. But also, you could have, what do we think? Maybe orange? Better. Okay. U spring in joules versus X should give us a quadratic. U spring in joules versus X squared in meters squared should give us a straight line. The slope of this U spring versus X squared should be 1/2 K. And then if we, let's see, what else do we care about? Maybe if we just did F versus X, not even particularly, for a spring, and we got some plot like this, yeah, then the area under is the change in energy, which we call work. Okay, so that's great. I'm going to stop this show and hope it helps you a little bit. Thanks.